Hello everyone. One of the main objectives of this channel is to draw young minds towards science and technology, because we strongly believe that drawing young minds towards science and technology tips the world a little bit more sharply towards leadership, responsibility, and for overall goodness of the planet. In this video, we are going to derive the expression for shear stress of an eye cross-section of a beam. Now, why would a beam tailored and fashioned to have eye cross-section? Because eye cross-section has greater resistance to bending. The resistance to bending is called the moment of inertia. You can see from the geometry itself that the beam accommodates more material at the outermost surface, as a result of which it can exhibit greater resistance to bending. It is like providing reinforcement at the outermost periphery of the beam. But remember, moment of inertia itself is just a geometric property. Now, let me tell you that if you look at this particular eye cross-section, it has got two prominent parts. The topmost part, which is called as the flange, and the part that is less pronounced, which is called as the web. Now, let me indicate the geometric properties here. The distance from the top portion of the flange to the neutral axis is capital D over 2, and the distance from the bottom portion of the flange to the neutral axis is small d over 2, and the breadth of this flange is small b, and the overall breadth of this eye cross section is this capital B. Okay. Now, what is the layer that is under investigation? The layer that is under investigation is considered here, because I'm interested in finding the shear stress at this particular layer, and this layer is considered at a distance of y from the neutral axis. Now, what is the formula to find the shear stress? Let me write the formula here. The formula to find the shear stress is tau is equal to F into A into y bar whole divided by I into B. Now, let me demystify this formula. What is capital F? Capital F stands for the shear force. Now, how can you get that information? By this time, I think that you know how to draw the shear force diagram. Once you know how to draw the shear force diagram, you can squeeze out the information of shear force at any particular point on your beam. So you know what is capital F. And what is capital A? A stands for the area above the region that is under investigation, which means it is this shaded area. So the layer, the area above the layer, that is what is called as A. And what is y bar? Y bar is the distance from the centroid of the shaded portion to the neutral axis. Let me say that the centroid of the shaded portion is over here. Look for that green color. And the distance from the centroid, which can be denoted by this symbol capital G, from the distance from the centroid to the neutral axis, that is what is called as the y bar. Okay, if you look very carefully at this particular formula, the term A into y bar itself is just area moment. It is area moment. Now, how do you find the area moment? First step always is to find the area moment. Once you get the area moment, you go ahead and plug it in this equation and turn the crank of mathematics, then you are done. You will get the expression for shear stress. Now, how do you find the area moment? Here we go. A into y bar, that is equal to area of the shaded portion. What is the area of the shaded portion? You see, height of the shaded portion is capital D by 2 minus y. I hope you got that point. You look very carefully. Give your undivided attention, and if you are very sharp, you will be able to identify that capital D by 2 minus y is going to be the height of the shaded portion. The length of the shaded portion is simply capital B, which I can write it here. So that is the area of the shaded portion, and y bar is the distance from the centroid of the shaded portion to the neutral axis, and that distance is the distance from, first let me write the distance from the centroid to the layer that is under investigation, which is going to be half of d by 2 minus y. I will say it one more time. The distance from the centroid to the layer that you are investigating, look at the highlighter, that distance is half of capital D by 2 minus y. So first I will write that down. It is just half of capital D by 2 minus y. That is the distance from the centroid of the shaded portion. That is, I'm talking about this particular distance. It is half of this distance. Okay, half of this distance that is given by that expression, because the total distance is given by this expression here. I hope you are able to understand that concept now. Okay, that gives you that distance, plus y will give you the distance from the centroid to the neutral axis. So I should not be forgetting to put that plus y. So this gives me the area moment, but I have to simplify this. Okay, it is capital B into, it is capital D minus 2y whole divided by 2 into, it is capital D minus, okay, minus 2y plus 4y whole divided by 4. I have just taken the LCM. So if you do it, if you just take 1 minute, you will be able to come to this particular expression. I have brought this 2 over here, and I have multiplied this 1 by 2 inside the bracketed terms to get 4 in the denominator. And if you take LCM, this 4 will also come over here if you take the LCM. So I get plus 4y, and the whole divided by 4 because I have taken the LCM. So if you look at this particular expression, this is capital D plus 2y. Capital D minus 2y plus 4y is capital D plus 2y. What is capital D minus 2y into capital D plus 2y? It is capital D squared minus 4y squared, because it is of the form a squared minus b squared. So in the next step, I'm just going to write that it is equal to capital B into capital D square minus 4y square divided by, so what is that? Whole divided by 8, whole divided by 8, whole divided by a. So this is the expression for a into y bar. All I'm going to do is I'm going to take this value and I'm going to plug it in the expression for shear stress. So the expression for shear stress is tau is equal to F into a into y bar. Instead of a into y bar, I'm just going to plug this expression. It is capital B by 8 into capital D squared minus 4y squared. Okay, that is a into y bar, whole divided by I into the breadth which is given by capital B, breadth of that particular layer that is under investigation. If I didn't tell you properly, I will say it one more time. This small b, I should not be writing it as small b. Maybe I should have to write that as the breadth. Okay, where breadth is the length of the layer that is under investigation. Maybe if I have to be even more precise, I will say it is the length of the layer that is under investigation. So I will simply write it as the length of the layer that is under investigation. So what is the length of the layer that is under investigation? In our case, it is capital B. So I have written this capital B in the denominator and capital B in the numerator. They cancel each other out. In the next step, tau is equal to F divided by I into capital D square minus 4y square. So this gives you the expression for shear stress. Now I'm going to just put a box. So this is the expression that gives you the magnitude of the shear stress. Now you can now plot a graph to find out how this shear stress varies, and this equation is valid from the point from the topmost part of the flange to the bottommost part of the flange. Okay, which means this particular expression is valid from this point to this point. And if you want to derive an expression for by considering a layer right at the web, well, you can do that, and the next video is all about finding the value of the shear stress at a particular layer by considering a layer at the web of the beam. So thank you all for your patience.